Thank you. Thanks for having me here. So today I want to talk about the Furstenberg entropy spectrum. So the setup is the following. So let's take G to be a locally countable or a countable group if you want. Then we choose some measure mu, some probability measure on G, which we think of as the step distribution of a one. And then so usually mu is chosen to be absolutely continuous with respect to half measure on G often, but it's not necessary to assume it at the very beginning. And now we can consider actions of G, measure the spaces. So we have some space X and measure nu. And then we say nu is stationary with respect to this measure. If it is invariant on average, mean you convolve mu with nu, then you get it back. So it's not necessarily invariant, but it is invariant on average under the random walk. So this is the definition. So if you want, you can write out the what the convolution means. So this is the integration of you move your measure and average, and here you act on measure in your usual way. Okay, so we start with a easy example. So let's take G to be just a free group on two generators. Then you can take your space to be the ends with the intercept at infinity. So let's take the space to be the boundary. These are infinite reduced words. And then we can choose a nice measure mu for the random walk. So we can do uniform generators and their inverses. In this case, you can take the stationary measure on X is a uniform with the Hostov measure on X. So you can easily check it is stationary, and this is one of the basic examples of a stationary action. And here you see on this space there is no F2 invariant measure, but there are natural stationary measures. And stationary measures always exist. So just remark if X is compact, then this kind of stationary probability measures always exist just by compactness. And so in the case where you don't have invariant measures, these are natural to look at. And by studying the structure of such measures, you might have some gain some insight into the action and so on. So this is one reason people look at this. And so we're going to look at the Furstenberg entropy of such measures. So this is by write down some definitions. So let's recall if you have two measures, let's say eta and nu, and we assume eta is absolutely continuous with respect to nu, then you can look at the KL divergence between these two measures. This is by definition, so it's just the log of the Nicodine derivative, and then integrate. So this measures how far eta is from nu. It is 0 if and only if this Nicodine derivative is 1. And then with the stationary measure, you can define the Furstenberg entropy. So here is the rapid notation, H for entropy, so X nu. And then, so for this, you can first think with respect to the random walk, if you take one step and move the measure, what is the divergence? Shift to the measure and do the divergence, and then you average according to the one step. So this is the definition of Furstenberg entropy of this action. And this number is an important invariant in the Poisson-Furstenberg boundary theory. It's related to, so if you look at the Furstenberg entropy of the Poisson boundary, it's related to random walk entropy. So this invariant plays an important role in the. Okay, so the question we're going to look at asks what is the range of numbers you can get by thinking about this entropy number of ergodic stationary systems with G and mu fixed. So you can add the following. So let's write entropy spectrum of this group G equipped with random walk measure mu to be all the possible ways I get by looking at ergodic mu stationary system. So here, even without the word ergodic, this is not interesting because you can always mix up systems. So your entropy numbers will be convex combinations. So it's to avoid the trivialities, we need to restrict to ergodic systems. And you can further restrict to smaller collections and ask what are possible entropy numbers you can get. So maybe some basic properties will make some more sense in a moment. So first, if mu is actually an invariant measure, then you get 0 for the Furstenberg entropy just by looking at the formula. So you always have a trivial actions. So 0 is in the spectrum, and if you take the Poisson boundary, the maximal entropy value, the Furstenberg entropy value is a 10th by the Poisson boundary. Of this mu random walk. You give it a notation, just write it as the letter for the space, and then the harmonic measure associated with the random walk. So here we do not need to recall the definition of Poisson boundary. It is some measure theoretical space that is introduced by Furstenberg to represent bounded mu harmonic functions. So you know this L infinity of this space via the Poisson transform represents all bounded mu harmonic functions. And because of that kind of universal property, it attains maximal entropy among all possible stationary systems. Okay, so we now know, so we're always going to assume that the random walk we consider here for the Poisson boundary, you get a finite entropy number. So we always assume that. Just make an assumption here. That's the Furstenberg entropy of this is finite. The standing assumption. So uncountable groups, we know that this number is exactly the same as the asymptotic random walk entropy. This also holds for locally compact case with some assumption on the density of mu. So this quantity is closely related to random walks. Okay, so now we know that this set is contained in the interval of 0 and then Furstenberg entropy of the Poisson boundary. So the next question, so the question you can ask is does this set sitting inside this interval have some structure? What kind of numbers you can see for these systems? And it shows some known results. One of the first results is by Louis Bowen. So this type of questions were considered in the work of Nevo-Zimmer back in the late 90s into early 2000s. It comes out of their systematic investigation into the structure of stationary systems. So we'll get back to this later. The first complete result was to Louis Bowen. Years ago, he said that if you consider the free group, so let's say for exactly this is the example. So you take a free group of two generators. This nice measure that you every time you choose uniformly A or A inverse. Then this is entropy spectrum is the whole interval. So this was the kind of biggest you can hope for to the Poisson boundary. You see the whole interval. And so the proof of this was kind of surprising at the time. So because when you look at this question, the first ideas might be maybe you look at quotients of the Poisson boundary and see what numbers you can get. It turns out to be quite challenging to fill the whole interval with the quotients of the Poisson boundary. So what he took was something like so the construction uses some, it's called Poisson bundles. Over invariant random subgroups. It's useful. So one property of these entropy numbers is that they respect the factors. So if you have a system X nu and you factor onto some system Y nu bar, then entropy is non-increasing. So so here you already have the Poisson boundary that's the biggest possible. So if you want to fill the interpolate between small values and big values, you can try to quotient out on the bigger boundary to get smaller numbers. So that's so it was done in the following way. So first you consider the space of closed subgroup. I guess here it's just subgroups. You consider the space of subgroups of F2, and then you put an invariant measure.
Excuse me, could you write a little bit bigger letters, maybe?
Yeah. So this is the invariant measure. And here F2 acts on subgroups by conjugation. And then you can consider the following bundle. So you take your subgroups. And then for each subgroup here, you put in the fiber. The fiber is the Poisson boundary of this cosine random walk. So you have random walk, say xn on F2. So just do this every time you choose uniformly one of your neighbors, and then you project it down. So this way you get a random walk on the cosine space. And it makes sense to take the boundary of that. Equivalently, what you take is the ergodic decomposition, the ergodic components of H acting on the original Poisson boundary, which is it's just the example over there. So this is the bundle structure. You have these subgroups, and in each fiber, you just consider these basically the bounded harmonic functions that are H invariant. So you mod out the full boundary by H, and then entropy should decrease. And the advantage of this is that so here you consider this space of invariant measures. So this is it's a affine space, so you can try to think: do you find a path, like a continuously parameterized sequence path of invariant measures on the space? And this way you can build a map. So he introduced some parameter p, where you can associate for each p some measure. So something, let's call it rho p. I mean an IIS, an invariant measure on the subgroup space. And then you take this measure and do this construction. So if you have some continuity, you can interpolate between different values. So this space of measures allows you to do this kind of interpolation.
So obtain any entropy, right?
Yeah, so he could obtain anything by varying P and varying P. So that's the idea. And this remains challenging to do if you do not allow some like the invariant part in your instruction. If you only ask for quotients of the Poisson boundary, then you cannot rely on extra things like this. And it's still open whether you can realize the whole interval or not. So this is the first result. Any questions? Good. Okay, so this is like a rank 1 example. It's some kind of rank 1 flexibility. So you can ask what happens for, if you choose your favorite group G, you can ask, does this set have some structure and so on. So the next thing I want to explain is what Nevo-Zimmer theorems tell you about the spectrum if you take G to be a higher rank simple group.
So if somebody gave you a group and a measure satisfying your properties, and you knew that this entropy spectrum is the entire interval, would you say something about the group? Would that tell you something about the group and its measure?
Yeah, it somehow shows you this group maybe is very flexible in some sense. It might have a lot of quotients, or it depends on how. I guess abstractly, if you know it's a full interval, you don't immediately get definite information. But if someone tells you how these are realized, it tells you it has a lot of stationary actions.
I mean, the fact that this guy was a free group, that helped in getting the interval.
That's true. So, but I guess you can't really scan algebraic information if you just know it's a full interval.
But maybe you will explain us now, your results give you some obstacles at least to have the whole interval.
That's from the Nevo-Zimmer theorem. That's good.
No, but
and there are other examples where you see the full interval. For instance, you take some Lamplighter groups on risk product. It's also known, yeah, but it's for different reasons from the free group. So let's see. Right, so the next thing to see is these Nevo-Zimmer theorems. So the first theorem is this well-known projective factor theorem. So here, let's take G to be a higher rank simple group. Yes, the theorem applies to semi-simple velocities with a rank simple elements. And then, so the first is the projective factor theorem. Tells you that so if, and here let's take mu to be what they call admissible. It means that it has a density with respect to the Haar measure, and moreover the support generates a group that's non-degenerate and in the Haar measure class. And then under this, if you have an ergodic stationary system, and nu is not invariant, then you would have a proper parabolic subgroup Q such that your X nu would admit G mod Q as a factor. So such that G mod Q. And then here you have the image of the harmonic measure. The factor of this system. So this is a very useful theorem. It tells you as long as your stationary measure is not invariant, then in fact you would have this projective factor. So we'll see how to use it to what it implies for this spectrum in a moment. And they also proved a lot of other theorems regarding stationary systems. Maybe just mention a few. So there is this. Well, here I guess I should mention. So it goes back to Furstenberg. So for this type of random walk, you know this G mod out the minimal parabolic is the Poisson boundary. Yeah, so I should say this first, and then it will make sense. So you take this random walk, and then from Furstenberg's original paper on Poisson boundary, you know G mod out the minimal parabolic equipped with the harmonic measure is the Poisson boundary. So there is a unique stationary measure on G mod P, and that is going to be the harmonic measure of the random walk. So this is mu stationary. This is a black variety, and you can show it's a unique one. So this is what mu P is, and then you map it, you push it forward under the quotient map to G mod Q. So these are all unique. Yeah. So actually on G mod Q, you also have a unique mu stationary measure. So these are what these notations are.
Yes.
Yeah, makes sense. Right. So this is the Poisson boundary, and then just by martingale convergence, you would obtain this boundary map. So there is a boundary map from the Poisson boundary into probability measures in your space. So this you can think of it as a decomposition of your stationary measures. So your nu is going to be decomposed into these. So for each point on G mod P, you obtain a measure, and then if you integrate it back, G mod P's, integrate it out, then you get back your stationary measure. So this is the boundary map. Boundary map always exists, but here it takes a very specific form that you map from G mod P into the space. And so Nevo-Zimmer showed that if you assume something additional about what you see in the boundary map decomposition, so there is a special one if you consider what is the image of the identity coset. This is the P invariant measure. So you can go between your original nu and this P under lambda by taking the decomposition or integrate it back. And then they prove that this is part of the Nevo-Zimmer works. So they show that if in addition, say lambda is a P mixing, then your system is actually a relative measure preserving extension. Sorry. Of your factors. In particular, if you add in this additional assumption, then you only see the entropy numbers coming from these G molecules, right? So that's because it's a relative measure presuming, so it's safe. So under this assumption, this additional assumption, the only entropy numbers you can see are just these factors of the Poisson boundary, the ones you expect to see. In particular, it's a finite. There are only 2 to the r of these. And you might ask, is that all? Is it always the case? They also answered no if you drop this. So, and so this is no longer true. So there are, you see, definitely many values you can see without additional assumption. Without this additional assumption. So that's with the of there. Yeah. So and then so the thing we wanted to understand is if you relax this condition, so you consider all ergodic systems. So Nevo-Zimmer already tells you you expect to see some flexibility. Can you see intervals just like in the free group? So that is the thing we wanted to understand. So it turns out for SLDR you can do it. So let's explain next. So we'll explain in the end why we only understood what happens on SLDR. So for other simple groups, there are some difficulties to understand what are the constraints. So next maybe explain. So so I want to explain what we know about this entropy spectrum for SLDR. So the statement is like this, so maybe I need to introduce some notations. So if you take G to be just the special linear group, then you know what the parabolics look like. It's here, I don't need to introduce a lot of notations. So if you take the Q to be a parabolic, you can think of it as a stabilizer of capital flag. But in matrix form, it looks like a block diagonal matrix. It's like you have some blocks near the on the diagonal, and then this up. We just want to introduce a notation. So if I have this matrix and define Q hat to be the parabolic subgroup of 10 from Q, by removing all the 2 by 2 blocks. You can describe it in slightly more rigorous way.
What this means.
Yeah, so this is not. Let me say it in a more precise way. Well, just maybe first do an example. So if I start with this parabolic in SL3, then so if this is Q, then removing this block means it becomes upper triangular. So more precisely, if
That was a star, not 0, though.
to get, oh, sorry, let's start. Yeah, so it says, so if Q, so more precisely, if Q is the stabilizer of standard flag, standard partial flag, say of a type, say let's write the type of the flag. Then for each I, we can such that say di plus 1 minus di is 2. That's responsible for a 2x2 block on the diagonal. We insert di plus 1 between di and di plus 1. So if you see like here,
So if you had the 4x4 thing with 3 and 1,
then you do nothing.
you do nothing.
Yeah, so that's only when you see the difference by 2, then you insert the middle one, and then and then take the stabilizer. So Q is the stabilizer of this longer flag. As a modified flag. So if you see a 2x2 block, then it becomes the upper triangular, and other places don't do anything. Makes sense? So yeah. Okay, so the statement, I can say statement is maybe first explain what if you use if you apply a Nevo-Zimmer argument. We can see the following. So suppose your system. So suppose in the maximal projective factor of x nu is G mod Q. So such a maximal one exists, and it's unique if you choose it in the standard form. And moreover, this Q has no 2x2 blocks. So Q, and you do nothing to Q. If you try to remove a 2x2, like these are required factors from the Levy subgroup, then it's actually, so you get the same conclusion as here, that it's actually a measure preserving extension. It's a measure preserving extension of G mod Q of this maximal parabolic vector. So the reason is that in this case, this description just means that on your diagonal, you only have higher rank factors in the Levy subgroup. And then if it is not a measure preserving, then you can run the argument again to find out that this is not the maximal projective factor. So this you need to somehow think through how to apply their argument, but it follows from the Nevo-Zimmer theorems. Okay. So it tells you if you can't do anything to modify your Q in this manner, then in fact your entropy are the same. So it's really that the Furstenberg entropy of the system is the same as the maximal projective factor. So this is the constraint essentially. Now Now it remains to understand what happens when you have the flexibility to kind of see this type of rank 1 things, and we want to see if you're in that kind of situation, can you do something similar to this statement that you see this 2x2 block is a copy of SL2R essentially, and F2 is the lattice there. So you expect this type of thing you can move it over to this, to sit above G mod Q. And that's exactly what we try to do. So maybe I state how much time do we have? 15 minutes.
25 minutes. It's a full
2 hour 50.
Full hour.
Well, okay. And so that's the statement. Maybe this is the statement with Brieussel. So it says the following. So we are in this. Just write the assumptions. So let mu be either. So this is what in Furstenberg papers it's usually called a B affinity. So it's a B compactly. We say there are two cases we can do. So either you can write say mu is in the power measure class, and the density is bounded and compactly supported. This is a technical assumption, so we want to see the Radon-Nicotin derivatives on the boundary are bounded, so that's condition. Or you can take it to be Furstenberg discretization supported on a lattice. So in the second case, you are actually looking at gamma action, but I just mention here that it's okay to like you can think about this kind of discretization to a lattice. Then we have the following. So if you look at, let's introduce a notation. So let's consider all these systems such that these are ergodic stationary systems such that G mod Q is the maximal factor of X. So consider all these stationary ergodic systems such that you admit this particular G mod Q as your maximal one. Then if you look at the entropy, possible entropy values from this set, the rest of the entropy spectrum, and you look at this particular set, and then here you see the entropy of the G mod Q, and then you can interpolate to Q hat. Here Q is not. This is not in the previous case. So here we do have 2x2 blocks on the diagonal, and then so this tells you if you consider systems that admit this G mod Q as your maximal factor, then maximal projective factor, then you can interpolate between the entropy value of G mod Q to this the one that's modified. So this is the statement, and the corollary. If you combine this with the Nevo-Zimmer constraint, then you can determine what is the entropy spectrum for SRCF. If you consider B affinity measure or you discretize it to a lattice, then as a corollary, you see for for this kind of example. What you see is a union of intervals. And here you go over your parabolics. And you see a union of this type of intervals. There are some G mod Qs where Q doesn't have rank 1 factors on the diagonal, and then they don't want to be moved. And then there are those that have some flexibility that you can interpolate to numbers. And this gives you the whole set of possible entropy values. So this is the description for SLDR. Choose.
So for these classical groups like SLDR, is it essential for you that you work over the real numbers, or could you replace the real numbers with something else like the p-adics or something?
Yeah, that's a very good question. So the Nevo-Zimmer theorems have been recently extended to other
fields,
p-adics or the Laurent rings. And so for us, the essential thing is that a free group is a lattice here. So as long as that is true, it's okay. But we do not, I'm not sure about replacing R by C, I'm not sure. But it works for p-adics.
for p-adics.
That's not, yeah, that's okay. But we do not know other, for instance, maybe write it as a question. We do not know what is the entropy spectrum for other, say, you can start with rank 1 simple groups, because these are the essential cipher building blocks for this. So this question, what is the entropy spectrum for say other means that except SL2R. Right. So in rank 1 we already haven't understood. So just to recall that so there are rank 1 simple groups that are that have property T. So if you take say SPN1, the hyperbolic Newtonians, or the exceptional one, the Cayley plane. So this has a property T. Then for spectral reasons, it's observed by Nevo. So if you have a property T, then 0. So property T implies that 0 is an isolated point. Is an isolated point in the spectrum. But this is rank 1, so the projective factor theorem doesn't give you abstractions for this. So we do not understand how to capture this phenomenon, that you do have more constraints on the entropy spectrum than given to you by the Nevo-Zimmer projective factor theorems. And so for this case, a priori you do not know about constraints, but having probability tells you that your next point must be away from 0. So what is this minimal rate, for instance? Is it explicit or mysterious, or so this is not known. And we also don't know are there further, like, do you expect to see an interval separated from 0, or are there more constraints above it? So this we do not understand in the classical rank 1 situation. And then even for SON1 with n at least 3, you cannot use the free group to do the draw. So it's already less flexible in some sense that you cannot do arbitrary things. So we do not understand what is the situation with these rank 1 examples. And then if you want to understand the higher rank ones, then you will see them appearing in the learning subgroup. So understanding these rank one simply groups are kind of necessary to further kind of understand the spectrums. Okay, so this is the main question I want to ask. Maybe some experts will have some ideas what to think. Yeah, so the main question, do you have, can we understand constraints other than given by this what happens with this? Okay, so that's the question. And in the remaining time, to sketch how to interpolate these kind of entropy numbers. So the idea is to induce from the free group. So we want to do something, we want to build some Poisson bundles with the help of random subgroups. And you already know from the various rigidity theorems that if you take, say, SLDR for higher rank, then you don't have invariant random subgroups other than the lattices or the trivial ones. And so you need to consider stationary random subgroups instead of invariant ones that Bowen used in the free group case. So it's necessary to consider. So we consider stationary measures. So these are called the stationary random subgroups. G. This is a fancy kind of I guess more probabilistic name. But what you're looking at is closed subgroups of G. And then you look for measures such that stationary. So you have fixed your measure mu. So like subgroups sampled from this kind of distribution are called stationary random subgroups. So just yeah, so we're somehow necessary to consider these kind of stationary ones instead of invariant ones, just simply because you don't have a supply for invariant ones. And then here, just maybe say, if you consider discrete ones, then there is a stiffness result of Rajik and Galender that tells you discrete subgroups. It is also stationary ones. It is stationary ones are actually invariant measures. Actually invariant. So you can't, so this somehow limits you, just know that if you restrict to discrete subgroups, then you also don't have a supply. So it's necessary to consider non-discrete ones. And for this, you do have a supply just by inducing from the free group. So you can do the following. So these you can start with a measure preserving action of F2. Say just write it as X0. So let's say this is the measure preserving for F2, and then you can induce it all the way to G. So you can do it because like I said, erased by the picture. So F2 sits as we have fixed our Q. So just illustrate how to kind of interpolate between Q and then the one that you filled, remove the 1 2x2 block to be upper triangular. So let's say that your Q looks like this. And then we first have, you can induce first to this copy of SL2R. modalize F2. So you first induce to that copy, and then you further think of your Q acting through the projection to this this copy. So this you can do. And then so Q acts through this quotient, and then you induce all the way to G. So this is a standard inducing procedure. And then you can take stabilizers of this map. So if the actions that I start with have existing stabilizers, then they will be carried all the way through to this side. And then you can easily see, because the way it's done, it's non-discrete, so it doesn't violate the homogeneity statements. So we take, and then you carry all your measures over by the standard inducing procedure. So this way, the stabilizers of this map gives you the stationary sector, which I'm just going to call it a rho. So it's induced from some system of free group. It makes sense. So that's now in the remaining minutes is to explain how you can build Poisson bundles out of this. So here, everything is somehow like relative to this G mod Q that's sitting there. And so finally, to build a Poisson bundle, what you need to do is to take a station. So in the when rho is invariant, when you build these Poisson bundles, if you think about it, what you started with is like some subgroup. And then you have your rho. If rho is invariant, you can just take a direct product with your random walk trajectory space. It's represents like your random walk trajectory space. And then this factors onto the Poisson boundary. So you can do this product and it remains stationary if rho is invariant. But if rho is now a non-trivial, like a non-invariant stationary measure, you can't do a product of two stationary measures is no longer stationary. So what you need is to take a stationary joining. I guess it's better to write the Poisson boundary here so that it's clearer. So you need a stationary joining. In general, you would need this boundary map to help you define the stationary journey. But if it's a specific construction, it's kind of clear what the joining does because by construction, it has the G mod Q sitting beneath. That is the part that you impose. So so in this case, we can build. So this stationary joining, from there you can take just essentially mod out some piece by the subgroup, and you get a Poisson bundle. It sits above the subgroup space. So this is the space that we're going to use to compute entropy. And in this particular case, we can do it in the following way. So for this particular example, the joining goes like this. So the system sits above, it factors onto G mod Q, and the rest is relative measure preserving. And then you can do the define the Poisson bundle as follows. So so if you let's call so if we call this map from this this is a vector map. Just call it a pi. So over a subgroup H that you factor onto. If you read where it sits, say it is a GQ. Then you take the random walk So this is the mu random walk, but you need to see this GQ at infinity. So it's a condition. This operation is called a dupe transform in potential theory. To it's exactly G mod Q. So you can kind of make your random walk to converge there. And then you project it down. So you look at, and then you take the Poisson boundary of this random walk. The point here is that H and this trajectory xn, they're not independent. They're coupled together so that when H sits above GQ, then this random walk is made to go to GQ as well. So that's what stationary joining does. And then with this, so this is how the bundle is being defined in this case. And then you can, once it's built, you can start to think about how your choice of row 0 is going to affect entropy of the system you eventually get here. And then with some analysis of the random walk, one can show the same kind of continuity argument here, the kind of continuity dependence on the input row 0. You can still carry it over and then get these paths that you need to interpret the intervals. So that's roughly how it goes. So it's a constructive proof, and it heavily relies on the free group. So if we don't know where to find the supply of subgroups and random subgroups, and it's not easy to think about what entropy values one can get. Yeah, so that's the limitation. It's our limitation is mainly that we rely on the free group. But if you have other ideas how to think about entropy, then different story. So I think I have to stop here. Thank you.
Do you know if are there any examples where the entropy spectrum is like infinite but discrete?
So there are examples from lattices that you can see the cantors that, yeah, but discrete, infinite and discrete, I do not know. But you can have holes like everywhere.
So if I'm not mistaken, it's a group property, whether or not there is a gap for the entropy spectrum. But do we know any examples where of groups which do not have property T, but there is a gap?
Somewhere. So it's I guess it's an interesting question. Does this gap at 0 characterizes property T? It's not known. So there is a result of, if I'm not mistaken, Bowen, Hartmann, and Tamu saying if you consider all non-singular actions, then having this gap is equivalent to property T. But it could be true that if you just look at the stationary ones, this gap also characterizes T. But then you can ask, maybe I have some, it's all accumulated here, maybe I have a gap here. Then I have no idea what that means. Yeah, it's not so well understood what the gaps in the spectrum. It must mean something, that there are certain entropy numbers that you cannot see, but it's not understood at all.
And for which groups, except for the free group, one can expect that any number in entropy spectrum is realizable as entropy of the random walk quotient.
So it's known for some risk products. So yeah, for Lamplatus, because
Isn't it different, no? Lamplata, you said you have this quantum set here, but for entropy of random
for
Lamplatus,
Lamplatus,
you wouldn't have a quantum set.
for Lamplatus, it depends on your choice of measure. Like yeah, it's for some examples you can do the whole example. Yeah, it's but I don't know whether how to understand seeing the full interval in terms of algebra. It's not clear at all. Yeah. So what you can read from this set is with no general results, except maybe this potentially is C property T, but yeah.
There are no other questions should be